Hello everyone, I am Dr. Shailendra Kumar, Assistant Professor in the Department of Electrical Engineering, Indian Institute of Technology, Bhilai. So, today we are going to see this introduction to EV charging station system. Under this particular topic, we will discuss architecture and working of EV charging. So, content for this lecture as EV charging architecture, we will introduce itself, then we will see overview of charging methods and topologies, what are the charging methods and how these EV batteries are going to integrate with the power supplies. Then we will see architectures of conventional EV charging stations, and then classification of solar PV powered charging stations. They are very famous as we are going to integrate these EV batteries with the renewable energy sources, and this type of charging stations, they are coming in very big way. Various configurations of EV charging systems, other configuration we can take wind, and we can take other renewable energy resources to power these electric vehicles, as well as this charging station we will see can it operate in standalone as well as in grid connected mode. Then we will see where it can be installed, right, and then summary of this particular lecture. So, let us start with EV charging architecture. So, there are various part of EV charging architecture as shown here. First one is power source. Power source is essential for any EV charging stations. If you have electric vehicle battery or EV at the charging station, so we need to provide power to these batteries, and these EV chargers are connected to the power grid or to the renewable energy sources like solar panels, wind energy systems. The power source can be alternating in nature, or it can be DC power we can take from the sources like solar PV, it is delivering DC power. However, if we talk about these power grids, they are providing AC power by which we can integrate these onboard and offboard chargers. So, we have basically two type of charger over here. We have AC charger, which it utilized as a onboard charger to convert AC from the grid to DC to the electric vehicle battery. However, these onboard charger, they are slow in nature and they are categorized under level 1. However, other type of AC charger, we have level 2 chargers, and they are categorized under semi speed, semi high speed kind of semi fast charger kind of thing, which used in homes as well as in public places. We have DC fast chargers. These DC fast chargers can convert AC into DC, and these chargers are outside from the vehicle. They are not inside the vehicle, as we have seen in case of onboard charger. Onboard charger, we need to carry it with the vehicle, or it is integrated inside the vehicle. However, these DC fast chargers, they are situated at public place, and we can charge our batteries from these public charging stations. They are quite faster as compared to level 1 and level 2, and they are coming under the category of level 3, and they require more complex infrastructure as compared to AC chargers. Then the next part of this architecture is communication system. Communication protocols are essential for this architecture, which enables interaction between EV and the charger. How much current we need to draw, what is the magnitude of current, as well as these charger, they have to communicate with the EV batteries, which may allow for function like charging control, status monitoring, what is the state of charge of the battery, what is the depth of discharge of the battery, other battery parameters, and user authentication. Communication protocols like open charge point protocols are also used in communication system. The another important aspect of this architecture is battery management system, which manage the battery charging, and it ensures it stay with the safe operating parameter. EV battery must not be overcharged and it should not be over discharged when we are operating in bidirectional case, and we need to maintain, we need to optimize efficiency, we need to maintain the battery life. Other important aspect that is known as grid interface. So, these charging stations, they must be interface with the grid, and it provides the energy whenever it is needed. Suppose we develop the charging stations and it is interface with the grid. So, whenever we have electric vehicle at the charging station, we can draw the power from the electricity grid, and these smart grid integration allows for demand response and load balancing also. So, if we see the overview of charging method and topologies. So, in last few classes we discussed about these overview. So, quickly I am covering it. Like charging method, we have conductive charging, other one is inductive, then we can go for battery swapping. So, in conductive charging, the most common method which involves a physical connection between the charger and the battery. In case of inductive method, it is also known as wireless charging, and it uses a simple electromagnetic induction to transfer energy from the source to the EV batteries. And we have battery swapping, where we can replace this discharged battery with the fully charged battery, which is available at battery swapping stations. Charging topologies, as we discussed, we have two type of charging technologies. One is onboard charging, which is slow charging, basically AC charging. Off-board charging, which comes under the category of DC fast charging, and it is located outside of the vehicle in public spaces or some big buildings. So, classification of EV charging architecture. These EV charging architecture has been categorized based on energy source, based on charger installation. Either we are going for a level 1 or level 2, slow, fast, moderate. So, they are also based on which kind of charger we need to install. Based on power flow, either we need to get unidirectional power flow, or we are going for bidirectional power flow, where it can be integrated as a G2V and V2G technologies. Based on level of charging, so it is level 1, level 2, level 3. So, as we discussed, level 1, level 2, they are AC charger. However, level 3 is a DC fast charger. Based on cable type, either we are going for AC connections or DC connections. Based on charger phase, so suppose we have onboard charger, and the battery unit is small, the power needed is only up to 3.3 kilowatt. So, we can go for single phase. However, if we talk about semi fast charger, then we need to integrate these level 2 with the 3 phase. So, as supply is available in single phase and 3 phase, so we can integrate the charger with the single phase supply as well as 3 phase supply. Here we have another topology for EV charging station, that is known as 3 phase 4 wire. So, whenever there is a problem of neutral current compensation or there is problem of neutral current. So, we need to compensate this neutral current when there is unbalancing from the charging side, because we are considering this battery as a load, we need to supply some power to these batteries. So, in that case we need to take care of neutral current and magnitude of neutral current, it should be mitigated. So, for that purpose we can utilize this 3 phase 4 wire topologies. So, this way, based on energy source, based on charging installation, based on power flow, level of charging, cable type, based on charger phases, I mean single phase, either we are going for single phase, 3 phase, these EV charger classifications has been done. Based on power flow, unidirectional power, bidirectional power, that is very very interesting concept where we can get this V2G and G2V, we will see in coming slides. So, here we have basic architecture of conventional EV charging station. So, in case of conventional charging stations, we have not integrated any renewable energy source with the charging station, and it is considered as a renewable, it is considered as a unidirectional charging systems, where the power to the EV is drawn from the grid. There is no facilities where we can operate these type of charging station in vehicle to grid mode. Nowadays, this type of technology is very famous to fulfill the peak load demand. Through aggregator, we can integrate all the EVs, and this aggregator will supply whenever there is huge load demand. This will inject the power at the point of common coupling, so that the burden on the electricity grid can be reduced. So, here we have two type of conventional EV charging station. The first one is common AC bus system and the second one is common DC bus system. So, you could find out over here, if you go from right to left, we have grid, it could be single phase or 3 phase depending on the requirement. Then we have a transformer which can step down the voltage up to some extent. So, one side we have medium voltage level, another side we have low voltage level. So, MV is step down to LV level, and then after converting this to low voltage line, low voltage level, at the AC bus we can connect these AC to DC converters, by which, because ultimately electric vehicle battery they need DC supply. So, if you have AC bus, this AC bus will supply AC supply, we can integrate onboard charger, but it will be difficult to get DC fast charging station. So, for that purpose we have onboard charger like AC to DC and then DC to DC conversion unit inside the vehicle, and they can be directly integrated at the DC bus. So, here we have given n number of vehicles which can be connected at the AC bus by using onboard charger. We have AC to DC and then DC DC stages. Other side, if we see, we have common DC bus based systems. So, if we go from the right to left, we have AC grid, and this medium voltage is stepped down to the low voltage, and then one centralized converter is used to convert this AC supply into DC, and we will get this DC bus. At this DC bus, we can integrate these fast charging type of vehicle, where we need to provide very high current and we need to reduce the charging time. So, these type of charging or common DC based charging, they are off board kind of stations, off board charging stations, and these DC stages could be people are using like isolated and non isolated converters to transform these DC power to the control DC, where we can control this charging current, discharging current when we are operating as a vehicle to grid and grid to vehicle. So, here grid connected charging station architecture, it offers two viable solution, where alternating current and direct current based systems. In the initial design, every load, every EV load is linked to the AC bus through an individual AC DC stage. This stage is integrated into secondary side of the step down transformer. The alternative design incorporates a single AC DC unit to provide unified DC bus service to the entire system load, entire EV loads which we have at the charging station. Moreover, the utilization of a standard AC bus is one potential approach to design the charging station. Every charging module is furnished with an individual stage of rectifier, which is linked to the secondary AC coupling point via a dedicated AC bus. So, what are the advantages of common AC bus architecture? It is very mature technology, cost effective, it uses a standard component. So, we have well established this on-board charging stations and on-board chargers which are with the vehicle, they are quite mature, and just plug-in approach is utilized to charge these electric vehicles. Highly available, the complexity of the protection device is low as the power level is also low, able to direct uses for local loads, stability and scalability are high. These can be scalable and they are quite stable. Reliable switching and control techniques. The control techniques to control these battery currents and the current which has been drawn, they are quite reliable. Ability to control active and reactive power. So, here if you see the charging stations, if you observe the charging station, conventional charging station, there are two stages basically, one is AC to DC and another is DC DC. So, DC DC stage is responsible to control the battery parameter. However, this AC DC converter or DC to AC converter can be utilized to compensate these reactive powers. So, this is the good thing whenever we are going to put these chargers, these converters in the charging station. So, we can also control these active and reactive power by providing proper switching signal through our control to these devices. And these devices are nothing but people are using for medium power level, people are using these IGBTs. Now, disadvantages of common AC bus architecture. So, these are slow charging, as we have seen mostly they are available as a level 1 and level 2, less efficient, complex with fast charging, on-board charger cannot handle high power. A large number of converters reduce rated power and efficiency. As soon as we will involve number of stages, as soon as the number of stages are increased, we will be having low efficiency to across these devices which are used for conversion from AC to DC and DC-DC. High cost due to multiple stages or multiple converters. Additional conversion stages are required for fast chargers to avoid harmonics. So, same converters can be utilized to mitigate these harmonics. Difficult to achieve high power quality and stability. If these converters are not controlled properly, we will realize the power quality which has been drawn from the electricity grid, that may realize there is some harmonics in the current and voltage. So, that kind of system we have to design so that it can also address the power quality issues. It is complex to integrate renewable energy sources and require additional DC-DC stage, because renewable energy source like solar, it is giving DC power, and in this case if you want to integrate these solar energy with the AC bus architecture, we require DC-DC stage for MPPT purpose, that is known as maximum power point tracking, and this DC-DC stage provide the duty cycle to the converter which we have utilized for conversion of DC power into regulated DC, and this converter will take care to take maximum power or to draw maximum power from these resources. Now, we will see advantages and disadvantages of DC bus based charging system. So, first we will see the advantages of DC bus based charging system. It is high efficiency of the charging station is high. DC bus is available. So, directly we can integrate these renewable energies sources at the DC bus. It provides high efficiency, high power density due to low component count. The control strategy is simple, low cost and flexible configuration which can integrate energy storage system and renewable energy sources very easily. It also helps to reduce the impact of high penetration of EV loads on the power grid. If renewable energies are integrated to the charging station, high peak demand, we can supply power from the renewables which can reduce the burden on electricity. And if we have installed energy storage system at the charging station, it can reduce fluctuations in the renewable energy. Disadvantages: require protection devices to withstand sudden changes, and also protections are very much essential for these DC based architecture, because the power level is very high. So, proper protection, without these proper protection we cannot establish these DC fast charging stations. The central converter needs server conditions, a communication protocols due to an increase in nominal power, increased complexity with multiple energy sources. So, as soon as we will integrate solar, we will integrate wind, we integrate other resources like fuel cell, then there will be a complexity. Every unit they need to communicate with each other, and accordingly they need to supply energy to the EV loads. So, energy management kind of control is also essential in the charging stations. Cooling arrangement during high power is also essential in these type of charging station. So, now we will integrate these renewable energy sources with the charging station, like we can integrate solar PV, wind into the charging station, which may reduce grid dependency, enhance sustainability, supports ancillary services, right. Power quality issues can be taken care during using these converters, DC to AC converters or DC to AC converter, they can take care of this power factor corrections and reactive power compensation. Challenges requires careful planning, control and management to ensure grid stability. So, whenever there is no power required by the EV batteries, suppose there are less number of EVs at the station, however, generation is more than the EV demand, EV battery charging demand, then extra energy can be injected to the electricity grid, which may ensures grid stability, but at that moment we need to control voltage and frequency at the point of common coupling. So, it could be challenge whenever bulk power is going to transfer to the grid. Under bulk power, we need to regulate these voltage and frequency parameter, I would say grid parameters at the point of common coupling. Growing interest in renewable energy sources, integrated charging station system for cleaner, cost effective EV charging. So, here renewable energy resources such as photovoltaic, wind, fuel cell and energy storage system that produce direct current electricity require an augmentation in the deployment of conversion mechanism within the power grid. It also illustrates the grid connected AC and DC bus charging infrastructure for EV charging, which serves as an alternative design for recharging EVs while processing the capability to generate substantial power. Given that renewable energy sources and energy storage device primarily operate on direct current, the DC bus present an opportunity to efficiently supply power to multiple charging unit, and the DC bus charging station exhibit a reduced number of energy conversion process as compared to the AC bus charging station. So, here there is classification of solar PV powered charging stations. Again, it has been divided depending on the number of supply phases. It could be divided into single phase, 3 phase, and then single phase can be divided into depending on the power stages. So, from renewable to the EV charging, how many stages we have, or from renewable sources to the power grid, how many stages we have. So, it could be categorized in single stage, 2 stage, we can have bidirectional power flow, unidirectional power flow. Other side if you see, this 3 phase can be divided into 3 phase 3 wire, 3 phase 4 wire, and further it can be classified into single stage, 2 stage and then unidirectional and bidirectional. So, this is the renewable energy integrated charging stations, where you can see PV array at the AC bus, it is coupled through DC-DC stage and then DC to AC stage, so that the power can be provided to the onboard vehicles. And along with this, one energy storage element we have also integrated. So, during outage of electricity grid, during outage of PV array, because as we can see night time sun is not available. So, we need to integrate battery energy storage in the charging station to provide uninterrupted power to the electric vehicles. However, other side we have a DC coupled stations, where the PV array is integrated via DC-DC converter stage, and it is coupled at DC bus. And then we have one central inverter through which we can couple this AC grid. Now, we have other charging stations where we can provide fast charging, slow charging, and then it is integrated with the wind and solar type of renewable energy sources. We have hybrid AC and DC charging systems. We can also develop a hybrid charging stations where these renewables are integrated, but other side we may generate with the help of renewable energy, we may generate hydrogen. If we have hydrogen based vehicle, these vehicle can also get some hydrogen from the charging station, and tank which is with the electric vehicle, that can be also filled by generating this hydrogen from the PV array or energy which can be drawn from the AC grid. So, for this purpose again one extra DC-DC stage is required to integrate hydrogen storage, or we can say for generation of hydrogen we are utilizing electrolyzer, and this electrolyzer is integrated at the DC bus via interleave buck converter, where this interleave buck converter can share the currents and we can increase the overall current capability of the converter. Then we have microgrid based EV charging infrastructure. We may have DC microgrid based EV charging infrastructure, AC microgrid based charging infrastructure, and these AC microgrid based charging station, they can be categorized into standalone and grid connected. So, here we have given a architecture of grid connected and standalone. So, at the when we have sufficient renewable energy and grid is available, at that moment the power can be fed to the EV from the PV array and from the grid as per their availability. However, if grid disappears, suppose there is some interruption from the grid side, the charging station can be operated in standalone mode, and at that moment we can supply EV power from these PV array as well as some onboard chargers. They can get the supply by converting this DC into AC at the point of common coupling, where a non-linear load is connected. So, plug in and initialization, then we have charging process. So, these are the few points which tell about the working of EV charging station. We need to control the power flow, we need to monitor, we need to control these devices, completion and disconnection, billing and authentications. Then energy management strategies are essential for EV charging stations, where we can assess the load demand, time of use, pricing. We can also pricing model can be developed for different electricity cost at different times. So, it has also be optimized so that customer may know at which time we are getting this less costly electricity. So, that we can get the reduced electricity prices, and that point of time customer can charge their vehicle, so that the wide adoption can happen among the customers. We have vehicle to grid integration, a smart charging algorithm, and then battery management system, which is also the essential part of this working of charging station. And then thermal management control must be integrated when we are operating the charging station. So, thermal management system in an EV is responsible for keeping the battery pack, power electronic devices and drives to their optimal working temperature regardless of external and internal temperature fluctuation. Thermal management plays a crucial role in the safety and usability of electric vehicles. Now, where the charging station can be installed? So, where here we can install the charging station in home, as we have seen home based solar charging station. So, at the roof of the home we can install some solar PV plant as per the availability of area, and we can get the power, we can charge these vehicles along travel routes in highways. We can also install these charging stations at offices. So, this is one of the example of residential charging. Tesla has developed the solar tiles for charging these electric vehicles. Then we have configuration for residential charging. We have home battery and this bidirectional charger which can charge the electric vehicles. So, with this, thank you for participating today lecture on architecture and working of EV charging stations. Here we have discussed various possible configuration for EV charging, and we also discussed, we explored how we can reduce the burden on electricity grid. So, integration of renewable energy resources is mandatory in case of electric vehicle stations. I hope this session has provided you with valuable insights and deeper understanding of configuration of electric vehicle charging station, architecture of electric vehicle charging station, as we have AC based architecture, DC based architecture. With this, looking forward to seeing you in our next session. Have a great time. Thank you. We have these few references which can be followed for